Somewhere in the south of Texas, on a stretch of land that barely existed on maps 5 years ago, a factory is being built with a single, almost insane goal: to manufacture one rocket per day. Not one per year, not one per month, one per day. To put that in perspective, the entire history of human spaceflight, every Saturn V, every space shuttle, every Soyuz ever launched, adds up to fewer than 200 crewed rockets over 60 years. SpaceX wants to match that number every 7 months. And the machine they've built to do it is unlike anything the aerospace industry has ever seen. By the end of this video, you'll know exactly how it's made. To understand why this factory matters, you first have to understand what Starship actually is. This isn't a satellite launcher. This isn't a cargo capsule. Starship is the largest and most powerful rocket ever built by human hands, taller than a 40-story building, capable of lifting 150 metric tons into low Earth orbit.
And designed to do something no rocket in history has ever done reliably: fly to space, come back, land on its launch pad, and launch again within hours, like a commercial airplane. The entire global rocket launch industry, every competitor combined, launches fewer payloads per year than SpaceX plans to launch with Starship alone. The market it's targeting is measured not in millions of dollars, but in trillions. Satellite mega-constellations, lunar missions, Mars colonization, and eventually point-to-point travel anywhere on Earth in under an hour. The question is not whether Starship will change the world.
The question is how they build it fast enough. Everything starts with steel. Not ordinary steel, a very specific alloy called 304L stainless steel, the same family of material used in surgical instruments and industrial food processing equipment. When SpaceX first announced they were building a rocket out of stainless steel, the aerospace world laughed. For decades, the industry gospel was carbon fiber and aluminum. Lighter, stronger, more expensive. Elon Musk looked at the numbers differently. Stainless steel melts at over 1400 degrees Celsius. At cryogenic temperatures, the kind you find when you fill a rocket with liquid oxygen at minus 183 degrees, stainless steel actually gets stronger, not weaker. And the cost per kilogram is roughly 100 times cheaper than aerospace-grade carbon fiber. The math was brutal and simple. Steel wins. The coils of 304L stainless steel arrive at the Starbase facility in Boca Chica, Texas, from mills in the United States and Europe. Each coil weighs tens of thousands of kilograms and contains enough material to build only a small section of a single rocket. To build one complete Starship, SpaceX needs hundreds of these coils. When you consider the production rate they're targeting, the raw material pipeline alone becomes a logistics operation of staggering scale. The first step in transforming raw steel into a flying rocket is ring rolling. Massive flat sheets of stainless steel are fed into automated cutting machines that slice them into precise rectangular panels. These panels are then rolled, literally bent by enormous hydraulic rollers into curved sections that will eventually form the cylinder of the rocket body. Each ring segment is only about 2 meters tall, which means a full Starship stage, standing nearly 70 meters from base to tip, requires dozens of individual rings stacked and welded on top of each other. The precision required here is extraordinary. A ring that is even slightly out of round, by a few millimeters across a diameter of 9 meters, will create misalignments that compound with every ring added above it. By the time you reach the top, a tiny error at the bottom has become an impossible gap. This is where things get interesting. SpaceX doesn't just weld these rings together by hand. They use a process called friction stir welding, driven by robotic arms that move along tracks surrounding the rocket assembly. Friction stir welding generates no sparks, produces no fumes, and creates joints that are actually stronger than the base metal itself. Traditional welding melts the material and refuses it, introducing heat-affected zones where the steel becomes subtly weaker. Friction stir welding never melts anything. It uses rotational pressure to essentially knead two pieces of metal together at the molecular level. The resulting weld is so clean and consistent that it barely registers under X-ray inspection. In traditional aerospace construction, welding is the weakest link. At SpaceX, it's one of their strongest. While the rings are being formed on one side of the factory, the nose cone and forward section of the vehicle are taking shape on the other. The distinctive pointed tip of Starship, the section that houses the payload bay, the crew cabin in future human missions, or the propellant tanks for the upper stage, is formed using a technique borrowed not from aerospace, but from automotive manufacturing.
Hydroforming. A flat steel blank is placed over a die, and then an enormous blast of pressurized fluid, water in most cases, pushes the metal into the mold at pressures that would crush a submarine. The result is a complex curved shape formed in a single operation, with no seams, no welds, and no stress concentrations. It's faster, cheaper, and stronger than building the same shape from individual panels. The heat shield tiles that protect Starship during re-entry are a different story entirely.
These hexagonal ceramic tiles, each one roughly 10 centimeters across, must cover the entire belly of the vehicle. Thousands of them, fitted together like a mosaic across a surface that curves in 3 dimensions. Each tile is slightly different from its neighbors. Each one must be bonded to the steel skin using a high-temperature adhesive that can survive the thermal shock of going from the cold vacuum of space to the superheated plasma of atmospheric re-entry, where surface temperatures exceed 1400 degrees Celsius within minutes. The installation of these tiles is one of the most labor-intensive steps in the entire manufacturing process, and one of the hardest to automate. For now, human technicians do much of this work by hand, one tile at a time, on scaffolding surrounding a rocket the size of a skyscraper. But the most impressive part of the entire operation, the piece of engineering that makes competitors lose sleep, is the Raptor engine. Every Starship has 6 of them on the upper stage. Every super heavy booster, the enormous first stage that lifts Starship off the ground, has 33.
33 engines firing simultaneously, generating nearly 17 million pounds of thrust, more than double the thrust of the Saturn V that sent humans to the moon. The Raptor is not just the most powerful rocket engine currently in production, it operates on a thermodynamic cycle so demanding that Soviet engineers attempted it for decades and never made it work reliably. It's called full-flow staged combustion, and it essentially burns every molecule of propellant with maximum efficiency, squeezing more thrust out of every kilogram of methane and liquid oxygen than any other engine design.
For years, American aerospace engineers considered full-flow staged combustion theoretically possible, but practically unachievable at scale. SpaceX is currently manufacturing Raptor engines at a rate that would have seemed impossible 5 years ago. The engine components are precision-machined from exotic alloys, nickel superalloys that retain their strength at temperatures hot enough to melt aluminum, copper alloys with microscopic cooling channels running through their walls, carrying liquid methane that absorbs heat before it burns. The turbopumps that feed propellant into the combustion chamber spin at over 100,000 RPM, faster than a dentist's drill, with pressures that exceed 300 atmospheres.
A single Raptor contains thousands of individual parts, and SpaceX needs to build hundreds of them per year. Assembly of the complete vehicle happens in a structure that looks, from the outside, like an oversized aircraft hangar, but inside functions more like a precision machine tool. The stacked rings of the rocket body are moved on enormous transport dollies, guided by laser alignment systems that track their position to within fractions of a millimeter. Cranes capable of lifting hundreds of metric tons lower upper sections onto lower sections, while teams of engineers monitor alignment from multiple angles simultaneously.
The nose cone is mated to the forward dome. The aft section, with its engine mount, designed to accept the load of 33 engines firing at full throttle, is attached last. The integration of the engines themselves is one of the most choreographed steps in the process.
Each Raptor is test-fired individually at SpaceX's facility in McGregor, Texas, before it ever sees a vehicle. Then, it's shipped to Boca Chica, inspected again, and installed into the engine mount using robotic arms that precisely align its fuel and oxidizer feed lines with the vehicle's plumbing.
One misaligned seal, one fitting that isn't torqued to specification, can create a leak that ends in catastrophe at T-0. The margin for error is not small. The margin for error is zero. Quality control at SpaceX doesn't happen at the end of the line. It happens at every step, simultaneously with production. Automated ultrasonic scanners travel along the welds, searching for microscopic voids. Photogrammetry systems, essentially arrays of high-resolution cameras, map the entire surface of the vehicle to create three-dimensional models accurate to less than a millimeter, comparing the as-built rocket against its digital design twin.
Pressure tests flood sections of the vehicle with inert nitrogen gas and monitor for the slightest drop in pressure that might indicate a leak too small for the human eye to see. Every weld has a digital record. Every component has a serial number. Every torque, every measurement, every inspection result is logged in a database that allows engineers to trace any part of any rocket back through its entire manufacturing history. And yet, SpaceX also accepts something that traditional aerospace companies have historically refused to accept: failure as a learning tool. The first several Starship prototypes exploded. On the pad, in flight, during pressure tests, SpaceX filmed every one of them, analyzed the data, fixed the problem, and built the next one faster. This philosophy, iterate rapidly, fail cheaply, improve constantly, is not recklessness. It is a deliberate manufacturing strategy. Every explosion taught them something that simulations and calculations alone could not. And because they were building with cheap steel instead of exotic composites, rebuilding was a matter of weeks, not years. Here are some numbers that are almost impossible to process. The Starship vehicle, stack complete, stands 121 meters tall, taller than the Statue of Liberty with its pedestal. It weighs 5,000 metric tons fully fueled. The Super Heavy booster alone carries 3,400 metric tons of liquid methane and liquid oxygen, more than the takeoff weight of a fully loaded Airbus A380, just in propellant. The factory at Starbase sprawls across several square kilometers. On a busy production day, the facility operates around the clock in multiple shifts. The steel supply chain feeding it requires coordination with mills across 2 continents.
The Raptor engine program employs hundreds of machinists and engineers at a separate facility 500 kilometers away. When all of this is running at full capacity, SpaceX estimates the cost to orbit per kilogram will fall to somewhere between $10 and $100, compared to $54,000 per kilogram on the space shuttle. That is not an incremental improvement. That is a different civilization. And then there is the catch mechanism. Because Starship is designed to land, not just the upper stage, but the 70-meter, 200-ton Super Heavy booster back on the launch mount, SpaceX built something called Mechazilla. 2 enormous steel arms, each weighing dozens of tons, mounted on a tower that is itself taller than most buildings. When the booster returns from space, falling at hundreds of kilometers per hour, these arms reach out and catch it, in mid-air, with no landing legs. The precision required is not engineering precision, it is surgical precision. A booster the size of a 20-story building, guided by GPS, radar, and onboard computer, threading itself between 2 arms with less than a meter of margin on each side. SpaceX has already done this successfully, more than once.
It is, without exaggeration, the most mechanically audacious thing happening in manufacturing on Earth right now. When a fully integrated Starship rolls out to the launch pad on its transporter, moving at walking pace, guided by a convoy of engineers and engineers with laptops, it represents somewhere between 6 and 12 months of manufacturing work across multiple facilities and hundreds of suppliers.
every weld, every tile, every engine, every seal, every data point. All of it moving together, slowly, toward a pad that will attempt to send it to orbit and bring it back in one piece, ready to fly again.
This is not the future of aerospace. This is what's happening right now in the Texas desert every day. A factory that started as a dirt field is now producing the most complex machines humans have ever attempted to manufacture at scale. And if it works, if the production rate holds, if the reusability holds, if the cost targets hold, it won't just change the launch industry. It will change what is physically possible for our species.
The age of mass-produced rockets has begun. If this video gave you a new appreciation for what it takes to build a machine like Starship, drop a comment below. What surprised you the most? Was it the friction stir welding, the 33 engines firing at once, or those steel-catching arms? Let us know. And if you want to see us go inside the factories behind the world's most extraordinary machines, submarines, fighter jets, the chips inside your phone, subscribe to Factory Automationverse. The next one will blow your mind even more.